So I told you I was going to get here before you, right?
Okay, I took my sweet time. Yeah.
Okay, let's see, what's the time? We can get started. All right.
Chester,
Yes.
either when are we gonna get the courses back, or will you post the answer key online?
Um, that's a good question. Um, by Monday you should get them back. Right? So for the answer keys, I think I'm thinking of changing my mind a little bit, so I'll be posting the answer keys. You know the reason why I didn't post it, so yeah.
For the exam as well, or
Uh,
for both?
for the exam,
Okay.
and I'll trust people this time around.
Wait,
Okay?
what's the reason?
So the reason I did not post the answer keys to the exam like I did last semester is because I had very unpleasant experience where students, after getting their exam back, went to change it, not knowing that I would detect that. And then they brought it back to me and were like, "Oh, I got this right," and you graded it as incorrect. That was so disappointing, you know. So that was the reason I stopped posting it.
Oh, but don't punish
So-
us because of some bad eggs.
But now I'm gonna make copies.
Yeah.
I'm gonna make copies.
Of our exams. Yeah.
Actually, we have a machine in the office now that can scan, so I can basically scan everything.
Yeah.
So,
And then compare.
yeah. So that solves the problem. All right, so let's get started. All right, so we've talked about the derivatives of carboxylic acid and the reaction they undergo. And we talked also about carboxylic acid and nitriles and the reaction they undergo. In those reactions, we were focusing on the carbonyl carbon as your reaction site, correct? So all the reaction we've talked about so far focuses on the carbonyl carbon as the reaction site, right? Okay, so we've focused on, let's call this X. Most of the reaction we've talked about up to this point on the carbonyl compounds or carboxylic acid derivatives and carboxylic acid focused on the reaction site being the carbonyl carbon. Now this time around, we want to look at the electronic nature of that carbonyl compounds and consider the reaction that can be conducted at another site other than that carbonyl carbon. Okay? So that's why this is referred to as carbonyl alpha substitution reaction. Okay? So let me just draw this out. Whatever X is, okay? This is your alpha carbon. Alright? So we want to consider the reaction that can be conducted at that alpha carbon. So we've talked about nucleophilic addition in aldehydes and ketones. So basically if you have an aldehyde, and you react it with a nucleophile, because there is no living group in there, that nucleophile will add onto the carbonyl. Or if you have a ketone, you guys can see the board, right? Okay. So if you have a ketone, your nucleophile can add onto the ketone am I doing? What did I do? I'm sorry. This is OH. Okay. So in these two cases, the nucleophile was added onto the carbonyl carbon because there's no living group, right? There's no living group in there. The only example where you have the hydrogen acting as a living group on the aldehyde is in the Cannizzaro reaction, correct? Okay, so you should remember that. That's the only exception. For the acyl substitution reaction, we have a carboxylic acid derivative. So let's what do we call this? Let's call this X. X in this case is not representing halide, it's just any group. If you treat that with the nucleophile is going to, because X is a living group, so the nucleophile is going to substitute that X. Okay? So, other than those reactions that you conduct at the carbonyl carbon, you can also conduct a reaction at the alpha position, like I indicated up here. So this is your alpha position to the carbonyl. And you can conduct electrophilic substitution reaction there, where you replace the hydrogen with another electrophile. So those reactions are called alpha substitution reaction. So here's a general example. If you have an alpha hydrogen, so this is the alpha position, you have alpha hydrogen. That alpha hydrogen can be replaced by the electrophile, the hydrogen, not the carbon. Okay. Now, this reaction can be catalyzed by both base or acid, and it goes through intermediate enolate ion or enol ion. Okay. You form an enolate. The mechanism go through enolate formation if you're using a base. But if you're using an acid, the reaction is going to go through enol formation. Okay? So you can either use base catalyst or acid catalyst. When you use a base catalyst, you form enolate. When you use acid catalyst, you form enol. We're going to talk about how that is formed. So it's after the formation of that enolate or the enol that your electrophile can add onto it. I'll give you the mechanism on the next page. So this is a concept that we've talked about, tautomerism, keto-enol tautomerism, that for every carbonyl compound that has at least one alpha hydrogens, they can undergo keto-enol tautomerism. So how does that occur? Well, your oxygen can pick up the alpha hydrogen, and the electron will be pushed to form a double bond between the alpha carbon and the carbonyl carbon, and your carbonyl double bond will break, leading to this enol. Enol because it's a double bond, carbon-carbon double bond, and all because you have an alcohol. Okay, so it's a very rapid reaction that occurs in every carbonyl. So for any carbonyl, if you have 99.5% of it in the carbonyl structure, you may have something percent in the enol form. Okay, so that occurs in every carbonyl, every ketone and aldehyde. Now let's look at how that enolate or enol forms. This is the basis for all the reactions under the alpha substitution reaction. Okay, you're going to form enol or enolate depending on whether you're using acid catalyst or a base catalyst. A base catalyst will give you enol, correct?
Enolate.
Very good. You're following the story. Good. All right. So let's look at the mechanism of the formation. Okay. So if your reaction is catalyzed with an acid, so HA is representing an acid. Could be HCl, HBr, anything. Okay. That's an example. So the first step is protonation of the carbonyl oxygen. That will further activate the carbonyl, and the carbonyl double bond can break, pushing the electron onto the oxygen, and that will place the positive charge on the carbon. Now your base would deprotonate the alpha proton, and the double bond will form. So that's how you get the enol tautomar. Okay. For the enolate, your catalyst is the base, right? So the base here could be any OH or any base, or methoxide, ethoxide, right? Any base. So that base, because of the acidity of the alpha proton, can remove that acidic proton, forming a carbanion. Actually, we should talk about the intermediate that's formed there. So this forms a carbanion intermediate, whereas up there it forms a carbocation intermediate. Let's go. Let's write it down. We have a carbocation intermediate. All right. So if you're using an acid, you get carbocation, a positive charge. If you're using a base, you get a negative charge. Okay. So that carbocation is resonance stabilized by your carbonyl, pushing the electron onto the oxygen. And the water that will form after the base picked up the proton is going to act as an acid now, protonating your enolate. So this is the enolate. So a protonated enolate is going to be enol. Okay. A protonated enolate is enol. So that's basically the mechanism that we'll be considering for all the reactions that we'll be talking about. Okay. All right. Any question? Okay. Oh well, we have to complete this by pushing the electron on the oxygen. Okay. Alrighty, so now let's look at the first reaction. Alpha halogenation reaction of aldehydes and ketones. Oh, by the way, I've uploaded the chapter 21 completed lecture notes on my courses, so if you guys need to review that, that's up there. Okay, so alpha halogenation. Now, a ketone or aldehyde with alpha protons can be halogenated using bromine or chlorine or iodine under acidic condition. And one of the hydrogen there will be substituted with bromine. Okay, so you change the hydrogen to bromine. If this is chlorine, then this will be chlorine. Okay. So what's the mechanism for that? The first step is activation of the carbonyl by the acid. So I'm just going to represent this as H plus. Acetic acid is, let's draw it out. That's your acetic acid. Okay, so I'm just showing the H plus in acetic acid. Maybe I should draw everything out. Okay, let's draw it. Because you may be asked to show mechanism. So that's your acetic acid. It's going to pick up that proton, and the electron will be pushed onto the oxygen. So you have stabilized by the carboxylate ion. So this will break. There's another resonance structure of that intermediate that places a positive charge on the carbon. Okay. I'm going to show one of the hydrogens here. Okay. So the acetate picks up the proton back, and you get your enol. So that enol is now going to react with your bromine. Let's go from here. So this is now going to pick the proton, and you get your free alpha bromo astrophenol. Okay, so that's how that forms. So if you use excess of that, it can keep on brominating that alpha hydrogen until all the alpha hydrogen has been substituted. Okay, and this is the basis of iodoform test, which you're going to do at some point in the lab. For the iodoform test for methyl ketones, you use an iodide, and that converts all the hydrogens in the alpha position to iodine. So you have Ci3, which is a very good living group, and you throw water into that, it gives you your carboxylic acid. But we'll get to that point at some point. Right? So that's mechanism. Any question with this? No? Okay. Now, there's a okay, if you have, let's say you have a competing reaction site, okay, like in this case, you have alpha proton here, then you have alpha proton on the other side. Because this is acid catalyzed, okay, your electrophile is going to add to the more substituted side. Okay? It's going to add to the more substituted side. So in this case, your bromine is going to go to this side. Alright. Now, what is the chemical significance of these alpha alloketones? They are called alpha alloketones, whether alpha bromoketones, alpha iodo-ketones, alpha chloroketones. What's the chemical synthetic significance of this? They are used to generate alpha beta unsaturated ketones when treated with a base. So what are alpha beta unsaturated ketones? Or aldehydes? Did I write that? Oh. Okay, so that's alpha beta position. Alpha beta position. Okay? Are you familiar with any method of making these alpha beta unsaturated ketones? Have we talked about any chemistry for making this alpha beta unsaturated ketone? What chemistry is that? Huh? What chemistry is that? We've talked about the reaction that will give you alpha beta unsaturated ketones. You did the reaction in the lab. Aldol condensation reaction. Right? They are connected. You did aldol condensation, right? Yeah, we did it. Right? So they are connected. So another way to generate alpha beta unsaturated ketone is to use aldol reaction of either aldehyde and a ketone with the corresponding carbonyl, right? So you generate the carbanion here by treating this with a base. And that base can add I didn't intend to write all this, but now I'm writing. So you get base, which in the presence of the base again can be dehydrated. You get to that. So alpha beta unsaturated ketone. So another alternative to that aldol condensation is this reaction of alpha haloketones with a base. So pyridine here is acting as a base. Pyridine or any amine. So what's the structure of pyridine? Pyridine is like benzene, but one of the carbon has been substituted with nitrogen. So that's pyridine. Okay? So this is pyridine. Okay? Or you could use any amine, so not just pyridine. They can use triethylamine. Triethylamine or any amine could be used. Okay? So what this base does, in this case pyridine, triethylamine is more basic, but pyridine is slightly basic, is it's going to remove this alpha proton. This will form a double bond and kick out the leaving group. So you have that alpha beta. So that's the significance of that.
Is there a methyl group on the alpha carbon?
Oh yeah. How many points are you taking off?
No.
I'm not trying that.
I just didn't know if it's one or something.
Yeah, there is a methyl group because there's a methyl group there.
Mhm.
Okay. Now, a question that is completely, it's connected, but it's something we've done in the past is how can you convert that alpha beta ketone to alpha bromo ketone? How can you go from the alpha beta unsaturated ketone from your right to the substrate on your left? What do you think you need to do? Huh?
Isn't it PBr3, BR2?
Well, PBr cannot react with anything there.
You do oxymercuration?
But oxymercuration is going to give you what?
Oh wait,
Oh, wait.
Oh wait,
Yeah, but then
you use like BH3 THF,
that's
and it gives you an OH minus, you get OH, and you use
Yeah.
PBR.
So that means you'll be going through the alcohol in
Yeah.
both cases.
Yeah.
Right?
What
But
does
that
that use?
so what do you do with the alcohol?
Use PBr3.
You use PBr. But so that's 2 steps, right?
You only use one
But is there one step that you can use to convert that to this?
It'd be HBr.
That's reaction of alkene, right? You do the HBr because it's acid catalyzed. It's going to go to the more substituted side. Okay, so you guys should think broadly. All right. Okay. So let's move on to the next reaction. We've talked about this reaction under carboxylic acid. If you guys remember, that one of the reaction carboxylic acid can undergo is reaction with the base to form salt and water. And then I gave another example of reaction I call it HVZ reaction. Okay. So the HVZ reaction, Hell-Bollard-Zielinski reaction, converts your carboxylic acid to alpha bromo carboxylic acid. Okay. So this is your reaction site, and let's draw the let me draw that so that's not messy. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6, 7. So one of these hydrogen here has been replaced . One, two, three, four, five, six, seven. 1, 2, 3, 4, 5, 6, 7. Now, if I want to be very picky, I will say the order of reagent they have here is incorrect. If I want to be very picky, why? Because your PBr3 should come first before the BR2. Okay? So just note that I don't know how Owl is going to arrange it for you. Okay? So what they have here, the order of that reagent 1 is incorrect. It should be PBr3 first before BR2. Okay?
Why?
Huh?
Why?
You see it in the mechanism now. The reason is because the PBr3 will first convert the OH functional group that you have in the carboxylic acid to Br, and that will make the alpha hydrogen to be very acidic so that you can remove it. Okay, so that's the reason. But you see it in the mechanism on the next page. And then the water is very, very crucial because that is going to convert your acid halide back to the carboxylic acid. Okay. All right. So let's look at the mechanism. So you can see that McMurray corrected his own mistake because this is what they used to have before. Okay. But if you look at the textbook now, they didn't put the BR2 here. They put BR3. Okay. So the PBr3 is going to convert this OH functional group to halide, to acid halide. And that is going to be followed by your acid catalyst that you need, which is going to activate your carbonyl to form the enol. Okay. See, it skips so many steps here. I'm gonna bring this down here to McMurray. We're already switching over. Okay, so you have H, E, R. Let's go there. So I'm this intermediate. That will be converted to the carbocation. So remember, you still have Br minus floating around here. So that Br minus is going to remove this hydrogen so that you can form your enol. Okay. So that is how you get to this part. So how many steps they skipped? So that's how you get to the acid bromide enol. So at that point, now comes in your Br2. Okay? Now comes in your Br2. So this will form a double bond. This double bond will break to pick up one of the bromine. Like that. Okay? So you get your alpha bromo acetic bromide in this case. Now the final step is treatment with water, which is going to act as a nucleophile to hydrolyze the acid halide, and you get your carboxylic acid. Okay. Right, so that's the HVZ reaction. Now, here's the question. Instead of using water here, what about if you use an alcohol? What do you think you will get? So, let me write this up here. We have so here we said you get the corresponding carboxylic acid if you use water. What will you get if you use an alcohol?
Sure.
Exactly, you get an ester. So this whole group replaces the bromine. Okay. So that's why it's always very good to understand the mechanism of every reaction you conduct, because switching reagent around can give you different things. Okay? Any question?
Yes, sir.
Yeah.
On the top, there's like a bromic acid step. Where did the bromic acid come from? Between the acid bromide and right.
No. You're saying how does this form, or what's the question?
It was Well, I was looking up top, the second step between the acid bromide and the
Yeah.
acid bromidenol.
Yeah.
Oh, I just wasn't sure where bromic acid came from, but it's,
Oh no. This is formed. It didn't come from here. So whenever you have bromine, you're not going to be adding bromine directly to your reagent. It's going to be bromine with some small amount of water, right? So you would definitely have HBr in there. Okay. So that's why you regenerate that as a catalyst at the end. Okay. Any other question? Yeah.
Could you move the paper up slightly, please?
Can I up or down?
That way, yeah.
Oh, okay.
Okay, thank you.
All right. Okay, so let's talk about the acidity of the alpha hydrogens. Okay, relative acidity of alpha hydrogens. So we know that a base can remove the alpha hydrogen to form a carbanion which is resonance stabilized from the enolate. So that means this alpha hydrogen is acidic, slightly acidic. The question is, how can you compare the acidity of the alpha hydrogens? We have a table that shows that, but before we get to the table, here's what we need to know. Treatment of your carbonyl with base will always give you a carbanion, right? The stability of this carbanion
I didn't hear what it was.
is that Siri? Siri, can you not speak when I'm speaking? They say Siri, right? Or can you give my lecture, please? And then I was listening. All right. So the stability of this carbanion determines the acidity of your corresponding carbonyl. Okay. If this carbanion is very stable, that means your carbonyl alpha proton is very acidic. Now, what stabilizes this carbanion? Electron withdrawing group adjacent to it stabilizes it. Okay? So if you have a carbonyl, that oxygen can pull away these electrons from this carbon because it doesn't want that electron on. The electron will be happier being on oxygen because it's electronegative. So this one is resonance stabilized, right? So what does that mean? That means the more of a carbonyl you have around the carbanion, the more acidic the corresponding alpha proton of that carbonyl is going to be. Okay, here we have one. What about if we have two instead of one? So that means we have base, we have this alpha proton, and then we're putting another carbonyl on this side. Okay? When you treat that with the base, you're going to get this carbanion, which is resonance stabilized to the right. Okay, and it's also resonance stabilized to the left. Let me just redraw this so that it's not messy. Okay. So the trick is the more resonance structure you can draw for a carbanion, the more acidic its corresponding acid is. Okay, so this is going to be more acidic than that. All right, make sense? So, and on that basis, you have this table. I think at some point you have to kind of just memorize them until you get used to them. Okay. So carboxylic acid, of course, is the most acidic of the carboxylic acid derivatives, followed by the diketone, which I just drew. So that has a pK of 9. When you change it to ester, when you change one of it to ester, that reduces the acidity. Okay, because of the electron donating effect of the oxygen of the ester. And if you have diester, it's even less acidic. Okay, so you probably have to play around with that table to basically memorize them. And when you have a single carbonyl in the structure, please pay attention to this. If you have a single carbonyl in the structure, the most acidic proton of that carbonyl is going to be for the aldehydes, right? So you can see that aldehyde here is more acidic than ketone, right? So that is why if you are doing aldol condensation reaction, for example, and you have a ketone and an aldehyde in there that has alpha proton, the alpha proton of the aldehyde will be deprotonated first because it's more reactive. So we can say the reaction will be chemoselective. Okay? Oops. Alright. So memorization to be done there. Sorry. Okay, so let's look at other reactions. So how many reactions have we talked about so far?
Like the whole world.
No, today.
Oh.
How many reactions? It looks like we've talked about a lot, but we've not, right?
3.
So let's recap. What was the first one? Huh? Alpha halogenation. Okay. And what's the second one? HVZ. And what's the third one? So we've actually talked about 2, right? So it looks like it's a lot, but it's not. It's just the explanation that's taking forever, right? And the mechanism. Okay. So now this will be like the third reaction that we're considering. Okay. Yeah, I think we've done 2, right?
Yeah.
Let me just check. I think we've done 2. Yeah. So alkylation reaction. Alkylation of your enolate or enol ion. So in the reaction of your carbonyl with bromine, what you're doing there is you're using your carbonyl as the nucleophile and your bromine as the electrophile, right? So instead of bromine, you can basically use any other electrophile, all right? And that's what we'll be considering now. What other electrophiles you can use in the same reaction instead of bromine? So if you have any polar covalent bond, if you have any polar covalent bond, the carbon of that polar covalent bond can act as your electrophile. Okay, so you can use that compound as an electrophile in any of this reaction. So your X can be tosylate, can be halogens, because they are good living groups. Okay. Well, if you have OH is a poor living group, but you can make it to lead by using a catalyst, right? So But to simplify it, we'll stick with tosylate and the halogens as the living group. What other living group do we know? Tosylate and halogens. What other living groups do we know? I'm trying to think. I think that's about it for now, right?
Ammonia?
Yeah, if you protonate it, it may be, but as NH2 it won't be. It will be a strong base. Alright, if anything come up to my mind, I'll let you guys know. Okay? So basically what happens when you treat your enolate with the electrophile is it's going to attack the electrophilic carbon, kicking out this living group. So this is a living group. So what example can we? Let's come up with an example here. Let's say you treat this with a base, KOH, for example, and you get your carbanion, which we know is resonance stabilized, but we're not drawing resonance structure now. And we treat this with methyl iodide, for example. This is going to attack that, and this out. Okay? Or let's say you use the same KOH or any base. Yes, your carbanion, and you treat that with, let's say, methyl tosylate. Okay? So that's a tosyl group. That's a compound. Okay? Alright. So that's one way to calculate the alpha proton. I mean alpha carbon. Oh, we have just 2 minutes. So we can use other electrophiles. We can use the carbonyls as electrophile if the carbonyl has a living group. Okay, and we're going to continue from there next week. So just think about this carbonyl that we have. The alkoxide over here and alkoxide over there are good living groups, and we're going to talk about the chemistry next week. Okay? You guys have any questions for me?
Do you have office hours today?
No. But if you come, I'll see you.